record on this computer. All right, so we are recording. So today we're gonna work on chapter 5. Chapter 5 is probably gonna be one of the toughest um, chapter that we're gonna get into, and it's not the math that's hard. It's essentially just both the vocab and also just reading the problem. That's where students kind of get hang up the most. You're being able to read the problem and be able to identify what type of formula we're going to be using. So for this one, you do kind of want to ask a question like, how do we know that we're using this formula versus the other formula? Because this section is going to be a tough section in regard to just reading the problem and being able to identify which formula we're going to be using. So let me switch over to my chapter 5 notes.
I promise the highest voice for press the high voice.
So in chapter 5, we're going to get started with probability. So in chapter 5, we're going to get started with probability. So probability, kind of already went over it when we went over to the empirical rule. If you remember for probability is telling you how likely or how unlikely an event is of occurring. So whenever we're looking at a probability, you kind of just want to know what does that probability tell us. So one thing about probability always telling you what the likelihood something occur in the long run. So this actually is called the law of large number. Because the thing is, whenever we find a probability, the probability is not telling you this is the likelihood this will happen in this outcome. It's kind of telling you if I do this outcome or this event many, many times, or if I do this experiment many, many times, what the likely probability is that you're going to get. Because the thing is, there's a short-term probability and then there's a long-term probability. So usually you want to use the probability, the long-term probability, because then you're saying if I keep repeating the event, it's going to be getting closer and closer to that probability. So up next, we're getting to this graph. So this graph is showing the simulation of flipping a coin. So for this one, what we want to do, we want to take record on the percentage of time that it lands on heads, or sorry, tails. So when we're looking for the law of large number, it's not saying, hey, this is a probability that could happen like in the first attempt or the second experiment. This is telling you if I repeat this event many, many times, like at the end, what that probability should be. But you kind of know it's not a guarantee. So if I do an experiment like 1,000 times, that doesn't automatically mean that 500 times it gonna land on heads, 500 times it gonna land on tails. What the probability telling me is saying it should be getting closer and closer to 50%, but it's not saying that it should be exactly 50%. So that's what this drawing is supposed to kind of illustrate. If you kind of look in the beginning, so the beginning, it's kind of right here. If you look at the beginning, you kind of see like a high variation. And the reason why you're seeing a high variation is because in the beginning, you're gonna have your data set gonna be volatile because you're gonna be getting where you get like tail, 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 and then you get like a head, and then you get tail, heads, tail, head. So you're not always gonna be getting like heads, tail, heads, tail, heads, tail. You're gonna be getting streaks in the beginning. But if you kind of notice, once you get a bigger sample size, And that's what this is kind of reflecting the bottom, is reflecting how many times have I flipped the coin. So if you kind of notice, probably like at this marker right here, you could kind of start noticing it started getting like a little bit less volatile. Because if you kind of look at the beginning, you have a lot of volatile where it's going up and then going down, up and down, up and down. But you can kind of see once they get like to, what is that? Once it gets to like 35 flips, you can kind of see it start hovering around 50%. But if you look at it, it doesn't eventually just settle at 50%. It keep on going up and down. It kind of hover around 50%. So it's not exactly 50%, but it's getting closer and closer to that 50%. So that's what the law of large numbers is kind of telling us. It's saying if I do a certain experiment many, many times, that probability should be getting closer and closer to 50%. All right. Any question in regard to the law of large number? So let's move on down. All right, so first definition for this one is we're gonna go over the definition of sample space. So that's right over here in case you're looking for it. And usually for sample space, the letter that we use to denote sample space is S. So if you ever see sample space or S, it just means the same thing. So with the sample space is essentially giving you all of the outcome that could possibly happen in that experiment. So let me see. So say if I have a die, and let me draw that out for you. If I were to have a die, and if you know a die has 6 sides. So it goes 1 through 6. If I want to find the sample space for this die, I have to see what are all of the possible outcomes that I could get from this experiment. So one of the outcomes I could get from this experiment is that the die could land on 1. I could also get that the die could land on 2. The other outcome that I could get from the sample space is that the die could land on 3, 4, 5, and 6. So our sample space is literally just listing out all of the possible outcomes that could occur in that experiment. So whenever we ask for the sample space, you just want to list out all outcomes that are possible in that experiment. Any question in regard to that first example about die? All right, let's go to the second example. So for the second example, it says a coin is tossed 1 time. What is the sample space? So we'll put S again. So in this one, what we want to do, we want to list all of the possible outcomes that could occur when we flip a coin. So one of the outcomes that could occur when we flip a coin, it could land on heads. Other outcome that could occur when we flip this coin, it could land on tail. And that's it. So that's my sample space, because since those are the only 2 options that could occur when I flip a coin, that will be my sample space. So let's do this next one. It says, what will be the sample space for a letter grade for Math 227? So assuming that you take the final, what are all of the possible letter grade that you could get for Math 227? So you can either put it in the chat. Oh, perfect. So you could get an A, B, C, D, and an F. Yeah, so that would be my sample space, because those are all of the outcomes that could possibly occur if you're going to get a letter grade in Mat 227. So we're not looking at which grade you want to get. Essentially, we're just focusing on all the possible outcomes that could occur if you're getting a letter grade in Mat 227. So it should be A, B, C, D, and F. Any question on that last question? So let's do this next one, and then we'll move on to something else. So for this one, it says a coin is tossed 3 times. For each toss, the possible outcome are head or tail. What is the sample space for this experiment? So for this one, it's important that they tell us you toss this coin 3 times. So it's not like the first one where they say they toss the coin just 1 time. So for this one, we want to pretty much take that into account that we toss this coin 3 times. So for this one, what you want to do, you want to use something called a tree diagram. So for the tree diagram, what we want to do, we want to list out all of the outcomes for the first attempt, the second attempt, and the first attempt. All right. So when I flip the coin the first time, what are the outcomes I could get when I flip the coin the first time? So, perfect, head or tail. All right. So that's my first flip. So now what I'm going to do, I'm going to flip the coin the second time. Filthy now. All right. So let's focus on this one over here. So say I flip the coin, and the first time I flip the coin, it landed on heads. So now what I'm going to do, I'm going to flip the coin again. So when I flip the coin again, what are my 2 outcomes that could occur? Yeah. So pretty much the same thing, head or tail, or oops, head or tail. All right, and that's it for the second flip. So what you have to do, you have to account that the first flip was heads. So when I flip the coin the second time, it could either land on heads again, or it could land on tails. Same thing for if the first time I flip it, land on tails, it could either land on heads, or it could land on tails again. All right, so now we're gonna go ahead and do the third one. So hopefully you kind of understand that the outcome are going to remain the same. So it doesn't really matter that the first time you flip the coin, it was head, and the second time you flip the coin, it was head. Like you still only have 2 options, head and tail. All right. So this is our tree diagram. So the tree diagram is kind of like a nice way to organize all of these different events. So that way you don't have to kind of look at it and try to figure out on your own what the events are, because pretty much we have a branch. So when I talk about branch, not branch. So this would be considered a branch. So if you look at for that branch, what are the 3 outcomes that I highlighted? Cool. So for my sample space, one of the outcome or one of the events will be H, H, H. So then say now I want to focus on this branch over here. How would I write that branch? Oh, perfect. H, H, T. All right, say I wanted to do this branch. How would I write that branch? HTH. So I'm gonna go ahead and just write out the rest. So HTT, THH, THT, THT, TTH, and lastly TTT. And I ran out of space. All right, so that will be my sample space. So if you look at this sample space, you have 8 outcomes. All right. And we're done with that one. Any question on how we did this one? All right, let's scroll on down. All right, so up next, we're gonna get into the definition of events. And just know for events, kind of think about it like when we went over numerical data set. And for numerical data set, there are 2 different types of numerical data set, where we have continuous numerical data set, or we have discrete numerical data set. Same thing for events. Events, we're gonna have something called a simple event and a compound event. But let's kind of go over what an event is. So an event is pretty much just listing out all of the different outcomes that you're looking for. So an event is when you're looking for a particular outcome to occur. So let's go back to letter grade in a Math 227 class. So for letter grade in a Math 227 class, we said that it's A, B, C, D, and F. So we said that was our sample space. So say if I wanted to find event, and usually for events, we usually denote the event by putting E. So we say E is equal to a passing grade. So we want to find the event of somebody getting a passing grade. So in my sample space, how many outcomes give me a passing grade? Go 3. So it should be 3 outcome. And that should be A, B, C. Cool. So an event may consist of 1 outcome or more than 1 outcome. So whenever we're looking for an event is saying, hey, we have our sample space, but we don't want all of the outcome in the sample space. The event, it kind of give you particular detail about what type of outcome are we looking for. So let's say I'm looking for E getting a A. So say if my event is getting an A, how many outcome in my sample space give me that? Cool. So 1. So we'll say 1 outcome. And the only outcome that gave me that is, well, you have to get an A in the class. So notice how some events are going to give you multiple outcomes. Some events are only going to give you 1 outcome. So that's where simple event and compound event come into play. A simple event is when there's only 1 outcome to your event. A compound event means there's more than 1 outcome in your event. So let's label this as A. Let's label this as B. Oh, that's an ugly B. So of my 2 events, which one will be a simple event? A or B? Cool. So yeah, perfect. So this is a simple event. The reason why it's a simple event, because this event only give me 1 particular outcome that satisfies this event. So that means A will be what type of event? There you go, compound event. All right, and that's it. So you kind of want to know the difference between a compound event and a simple event, because a compound event means there's multiple outcomes in your event. A simple event just means there's one outcome in your event. So like this example, if I tell you we are only looking for getting A, pretty much that would be a simple event because there's only one outcome that satisfies that event. But if you look at event E, which is passing gray, and this one, since we have 3 outcomes, that's why it will be considered a compound event, because there's more than one outcome that satisfies this event. All right, so let's do some of the example I have here. All right, so for this example, say you flip a coin and it land heads, the event will be heads and will be written as H, which is equal to head. So for A, now say the coin is flipped 3 times and the outcome are heads, tail, heads. How would you write this? So if the first time I flip the coin, landed on heads, second time I flip it, landed on tail, third time I flip it, landed on heads. So how would I write this event? Oh, perfect. H, T, H. So the event is that the first one land on heads, second one land on tail, third one land on heads. So for this event that I have right here, would that be considered a simple event or would that be considered a compound event? Cool. All right, so we're having a battle of the compound versus the simple event. Well, if I look at this, how many outcomes do I have here? Well, why 3 or why 2? Well, isn't this describing one event? Because if you look right here, it said we flip the coin 3 times. So if I flip the coin 3 times, if I get heads, tail, heads, that's describing one outcome. Because you're describing that we flip the coin 1 time. Well, sorry, we flip the coin 3 times. We get head, tail, head, but it's only describing one outcome. So this is technically one outcome. So this one is actually a simple event. So this will be a simple event because there's only one outcome that will give me heads, tail, head if I'm flipping a coin 3 times. Okay, kind of going back to this one over here. If you look at it, heads, tail, head is this one event out of the 8. So that one you should have says simple event, not a compound event. Any question in regard to B? All right, let's do C. So for C, it says now instead of looking for the outcome of heads, tail, head, I just want there to be 2 heads and 1 tail. In this case, the order doesn't matter, so let's write out all the different events. All right, so for this one, you're saying, I don't care how I get the order. I just care that at the end, when we flip the coin 3 times, I want there to be 2 heads and 1 tail. So we already know one of the ways that we can get 2 heads and 1 tail, and that's by getting heads, tail, heads. But is that the only way I could get 2 heads and 1 tail? What's the other way I could get 2 heads and 1 tail? Sweet. Thanks, Stephanie. So heads, heads, tail, or you could get tail, heads, head. All right, good job. So that's my event. So I could either get heads, tail, heads, 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 tail, or tail, heads, heads. All right. So let's do D. So for D, is C a simple event or a compounding event? Yeah. And we're done. Compound. All right. And that's it for the last problem. Well, you can get telltale heads because if you look at that one, it's not satisfying that we want two heads, one tail. So if you look at that case, you have two tails, one heads. So that way telltale heads wouldn't work because you want there to be two heads and one tail. Okay. Any other questions? All right, let's scroll on down. All right, so let's go ahead and do this problem. So for this one, it says consider the experiment of a horse having two foals. So foals are just baby horses. So for part A, it says what are the possible gender outcome when having a foal? So when a horse have a baby horse or a foal, what are the outcomes that could occur gender wise? Yeah, so you could either have a male or you could have female. Good job. So for part B, it says, are these two outcomes equally likely? Yeah. So we're gonna go yes. It is equally. Sweet. All right, so C said determine the sample space. So let's determine the sample space. So for this one, what are all the possible outcomes? And if you look right here, it says we're having two foes. So what are all of the possibilities that could occur if we're having two foes? So we have two of them. We're still missing two more. All right, cool. So we got male, male. All right, good. We got female, female. So if you look right here, we have four outcomes. All right. So that's our sample space. So our sample space for if a baby horse, or sorry, not baby horse, but if a horse is having two foals, the possible outcome that could occur is that it could be a female, 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 male, male, female, or male, male. So let's go to part D. So for part D, it says define the event E is equal to having one boy or a colt. So for this one, we only want them to have one boy. So let's do E. How many events or which of the four events satisfy having one boy? So none of them at least give me one boy or one male? Ooh, well, now you're giving me too many. Well, let's look at this one. So, did this one give me one male or one boy? Okay, good. No, that one does not give me one male. What about MF? So, what about male, female? Does that one give me one male? Yeah. So, right now we have MF in here. What about FM? Does that give me one male? All right, last one. What about MM? Cool. So for this one, the correct answer is no. MM would not categorize as having one boy because MM is actually two boy. So for this one, you have to be careful with the wording. Oops, erased a little bit too much. Yeah, sorry about that. So for this one, you have to be careful with the wording because if it says one boy, you want it to be exactly one boy. If they would have said one or more boy, then you want to include MM because it's saying you can have one or more than one, which would be considered to have two boy. All right, so that's it for part D. Any question in regard to part D? All right. So for this one says for the event in part D, would it be considered a simple event or a compound event? So would this be considered a simple event or a compound event? Good. So since I give you two outcomes, this will be considered a compound event. Compound event. And we're done. All right. Everybody good so far for this? All right. So far, what you should have gotten is you should know, or you should hopefully be able to understand a sample space. You should be able to identify an event, and you should be able to identify a simple event versus a compound event. So far, that's what we have done. All right. So up next, we're gonna go ahead and do something called rules of probability. So when we do rules of probability is saying these are the rules that your probability should follow. So telling you once you find a probability, or once you have all of the outcome for the probability, like these rules, like your distribution should follow these rules. So the first rule is this one. So maybe some of you don't know about inequality or you had a hard time reading inequality. So what this is telling you, probability should be between 0 and 1. And it could be included 0 and 1. So pretty much what this is telling you, can you just kind of remember a probability? A probability, we usually write it in a decimal form. So if you write it in a decimal form, it is saying it has to be between 0 and 1. If we're doing this as a percent, then we could say it has to be between 0 and 100%. But usually we work with decimal form. So for this one, we're going to say between 0 and 1. So that should kind of make sense to you because you should kind of know there is no probability above 1 because we're never going to find a probability, I guess, say is equal to like 1.1 or 1.2 or 3 because that would mean like it's going beyond 100%. And pretty much it's either going to be 100% or it's going to be 0%, but it shouldn't be anything higher or lower than those two values. And also, we should never have a probability that's in the negative. So if you ever find a probability and it's telling you that it's negative like 10%, negative 20%, negative 100%, something is wrong because it can never be a negative value. So this first rule is saying that the probability of an event has to be strictly between 0 and 1, including those values. All right. Any question in regard to the first rule? All right. second rule. So the second rule, go back to a sample space. So if you remember sample space, we list out all of the outcomes. So each one of those outcomes, we call them individual events. So if you look right here, that's what I'm doing. I'm just identifying that each one of those outcomes is an individual event. Because remember, there's a simple event and then there's a compound event. So where it says E1, E2, all the way to EN, it is representing simple events. And it's saying these are all of the events that could occur in a sample space. So since these are all of the events that could occur in the sample space, what we're saying, if I add up all of the probability of those individual events, since these events are all of the events that could possibly occur, it should always add up to 1. So that's the second rule. The second rule, you say if I add up all the individual events, or if I add up all of the probability of the individual outcomes, these should always add up to 1 or 100%. It's never going to be, like for this class, it's always going to be equal to 1. If you get something like 1.1 or 0.99, pretty much you would say it doesn't meet that rule. So for this one, it could be strictly, it has to equal to 1. If it's above it or below it, the rule have been violated. All right. So those are your two rules. So the first rule, you're saying that the probability has to be between 0 and 1 strictly. And the second rule said if you add up all of the probability for all of the individual simple events, these should always add up to or equal to 1. Any question in regard to the rules before we move on? All right, let's get started. So for this one, says the table below shows the ABO and the RH blood type frequency in the United States. Check to see if the rule of probability are satisfied for the table below. So right here saying rules of probability. So that means we have to check to see if this one is accounted for. And we have to check to see. So these are the two rules we're going to check. So we have to check to see if each individual probability is between 0 and 1. And we also have to see if we add up all the probability, does that add up to 1? So let's go ahead and look at it. So if you look at 0.357, so right now we're focusing on this rule right here. So does 0.357 fall between 0 and 1? Cool, yes. So we check that off. All right, let's go on to the next one. What about 0.063? Does that fall between 0 and 1? Oh, we're 2 for 2. What about 0.085? Does that fall between 0 and 1? What about 0.015? Does that fall between 0 and 1? There, yes. What about 0.035? What about 0.006? What about 0.374? What about 0.066? All right, since each individual probability fall between 0 and 1, that's how you check that first condition. All you have to do is see, does all of the probability are between 0 and 1? Pretty much this one should be pretty simple to see. If you have anything above 1.1, or sorry, anything above 1 and anything below 0, then automatically this rule is failed. And the thing about this, the probability rule, if one or both of them are violated, then you say this does not follow the probability rule. So it doesn't matter if one of them does meet it, but the other one doesn't. As long as one of them doesn't meet it, pretty much the whole thing doesn't work. So both of them have to work in order for us to say that it does pass the rule of probability. All right, so let's go ahead and do this second one. So to check the second one, all you have to do is just add up all the number. So we're gonna say 0.357 plus 0.063 plus 0.085 plus 0.015 plus 0.004 plus 0.006 plus 0.374 plus 0.066.
Guess what, guys? I came to dinner tonight without a purse. I don't have any money. So cute. I do. I have a talk show, so it's my treat. What time do you?
That works. All right, so if I add up all of those numbers, what do they all add up to? Cool. 1. So since they all add up to 1, this one also checks out, and we're done. So for this one, it's asking check to see if the rows of probability are satisfied for the table below. We'll say yes, the rule, oops. And we're done for this one. Any question on how to check the rule of probability? It's pretty simple, but for those of you kind of mentally remind yourself, you have to check both conditions because sometimes students, they get focused on just one of the conditions that they forget the other condition. So when you're doing this, just kind of remind yourself, you have to check to see if all of the probability are between 0 and 1, but also you want to check to see when you add them up, that they add up to 1. All right, so let's do this definition. So this definition is kind of telling you like anytime your event probability is equal to 0 or your event probability is equal to 1, it's kind of mean it's guaranteed. So if your probability of the event is equal to 0, it's guaranteeing you that this event is not going to happen. So anytime the event has a 0% chance of occurring, that's telling you this is guaranteed that's not going to happen. Anytime the probability of the event is equal to 1, that's a guarantee that it is going to happen. So anytime these are kind of like the two extremes, 0 and 1, 0 means it's guaranteed not going to happen. If anything is ever equal to 1, or the probability of the event is equal to 1, it's guaranteed that it will happen. So you kind of know that for later. So anytime it's equal to 0, guarantee that's not going to happen. If it's equal to 1, it's guaranteed that it is going to happen. Or impossible. So up next, we're going to go ahead and we're going to go ahead and build a probability model. So in order to build this probability model, we're going to use this table. So we have the color of M&M in a fun size bag. So the colors are brown, yellow, red, orange, blue, and green. So these are all of the outcomes that could occur when we're getting M&M from a fun size bag. So if you look at it, we have the frequency, and now we have the relative frequency. In order for me to calculate the relative frequency, how would I calculate the relative frequency? This is going back to chapter 2, when we did histogram. So how would I calculate the relative frequency?
Add them up and divide by 6.
Well, you're right about the add them up part. So let's add them up. So we could do 9 plus 6 plus 7 plus 4 plus 2 plus 2. So we get a total of 30. Cool. All right, so yeah, so if you look at the chat, Alejandro said divide them by the frequency. So for the first one, what we're gonna do 9 divided by 30. I'm gonna do that on my calculator. So we'll do 9 divided by 30. And you get 0.30. All right, so let's do the next one. So for the next one, we'll do 6 divided by 30. So say 6 divided by 30. You get 0.20. Let's do the next one. 7 divided by 30. 7 divided by 30. You get 0.23. So let's do orange. Orange will be 4 divided by 30. So 4 divided by 30, you get 0.13. Then what we could do 2 divided by 30. 2 divided by 30, you get 0.06. Well, actually, for this one, we're going to round it up to 7. Okay, if you do 2 divided by 30, you should get 0.066666. But since we're just using 2 decimal places, the 6 is going to round up the 6 to a 7. So that'd be the same thing for this one, 0.07. All right, so that's how you get the relative frequency in case you've forgotten how to get the relative frequency. Cool. And also, if you look at this, all of these probability are between 0 and 1. And also, if you add these probability up, they add up to 1. So that's how you know this is a probability model, or it follows the probability rule, because all of the probability are between 0 and 1. And also, when you add them all up, it add up to 1. So any question on relative frequency? All right, sweet. So I'm going to do part A. So part A says, what does randomness has to do with probability? So the thing is, like, whenever we get a probability, this probability is telling you, like, if we randomly select these objects. And not saying, like, if we cherry pick these objects, because kind of think about it like going to these M&M fun bag or fun size bag. Like, if you only eat red M&M and you're going to be cherry picking all of the red M&M, so the probability that you select the red M&M is going to be 100% because you're only looking for those red M&M. But if you're just kind of like diving your hand in there and just randomly selecting these M&M, that's what the probability is telling us. The probability are telling us like which one are more likely to occur, given that we are doing that random selection. So whenever we're finding a probability, the probability is telling us this is the probability this occur if we're randomly choosing, not if we already know what we're looking for. So that's what the randomness has to do with it. It is saying like if we're randomly choosing these data set or these M&M in this case scenario, this is how likely these events are to occur. So let's say what's the number? All right, so let's do B. So for event, for B, it said what event had the lowest probability of occurring? So what outcome or what color had the lowest probability of occurring? So blue and green. All right, so blue and green. So both blue and green have an equal chance of not occurring because both of these are the lowest one. So for part C, it says, does that make it impossible to occur? So since it has the lowest probability of occurring, does that mean it's impossible for it to occur? Yeah. So we'll say no, since okay, remember, in order for something to be impossible to occur, the probability of that has to be 0. So since both blue and green have a 7% chance of occurring, it's telling us these events could occur, but the thing is, it's not as likely as occurring as say brown or yellow or red, but it's still a possibility that these events could occur. So whenever we're looking at the probability, it is telling us how likely these events are occurring, but it's not telling us that it's impossible to occur, because the only time it could be impossible to occur is when it has a 0% chance of occurring. So that's the one thing you kind of have to just know for probability. Just because it has a low percentage doesn't mean it's unlikely to occur. It could still happen. It is saying like the chance of it occurring is not that very high. All right, and that's it for that one. Any questions for the last problem? Oh, went too high. All right. So up next, I'm gonna give you a definition for the class. So this is the definition we're gonna be using for like tests and quizzes. Because usually for tests and quizzes, I usually like to ask you like, is this event unusual? So whenever we say unusual, unusual just means that like the chances of this event occurring, like it's not very likely for this event to occur. So whenever we use the word unusual, it's telling us like the chances of this event occurring is not that very high. So typically the rule of thumb that we're gonna use for this class, we're gonna use the 5% rule. So if an event has a less than 5% chance of occurring, we're gonna say that that event is unusual. So anytime if you get a percentage and that percentage is less than 5%, and if I ask you, is this event unusual? All you have to do, you put yes because it's less than 5%, or yes because the event has a less than 5% chance of occurring. So yes, no, for our class, that's gonna be the definition of unusual. Anything less than 5% is gonna be considered unusual. But outside of class, pretty much we all kind of have our different case on what should be considered unusual. Because some people might feel happy or not happy, but they'll be satisfied with a 5% or less than 5% chance of this occurring. But other people might not be that comfortable with a 5% or less than 5% chance of that occurring. So what we're gonna do, we're gonna go over two events and we're gonna see what do these two events tell us. So let's look at the first one. The first one says the probability that the airplane have turbulence is 4%. So that's one event. So we'll call this event 1. The second event is the probability that airplane crash is 4%. So we'll say that's E2. So if you notice, both of them, we're using 4%. So in both cases, in this class, they're considered unusual because it's less than 5%. So in our class, we'll say these events have such a low probability that we consider them unusual. But let's kind of describe what does this represent. So for part A, it says let's describe what does the probability mean in both case scenario. So let's look at case scenario E1. So when I say it has a 4% chance of occurring, what is that telling me? Well, let me kind of help you out with the first one. So if we have 100 airplanes, so if I have 100 airplanes, how many of these 100 airplanes should I expect to get turbulence? Oh, perfect, yeah. Pretty much the easy way to kind of think about this, percentage is per the 100. So whenever you find a percent, so 4%, it's telling you 4 per the 100. So easy way to do percent. If we have 100 airplane, we should expect, gotta erase that. All right. So for this one, for event E1, we'll put if we have 100 airplane, we should expect 4 to have turbulence. What about for event 2? So for event 2, we'll write the same thing because so if we have if we have 100 airplane, how many of these 100 airplane should we expect to crash? Sweet. All right, so this is what the 4% is telling us. So in one event telling us, hey, if we have 100 airplane, we should expect 4 to have turbulence. The other event is telling us if we have 100 airplane, we should expect 4 to crash. So for part B, it said, are you okay that both of these scenarios are 4%? So let's go to E1. So for E1, playing with the turbulence, are you okay that that's 4%? That has a 4% chance of occurring? All right, so most of the class says yes. So we'll put yes. All right, so what about for E2? So the probability that airplane crash is 4%. Are you okay with that being 4%? All right, so we have overwhelming no. All right, so let's go on to part C. So it says, would you want one of the event probability to be less than 4? Why? 4% why? So of the two event of E1 and E2, which of them would you want to be less than 4%? E1 or E2? All right, E2. Well, why E2? Why not E1? Because both of them are unusual events. So why are we not happy with E2 being 4%, but we're more than okay that E1 is okay? Well, I never said you're gonna die. You said I'm gonna crash. You could survive a crash, maybe. Oh yeah, so like the reason why we're not comfortable with E2 being 4% is because like 4% is still pretty high for an airplane crash versus like a turbulence, that's okay because that's not like life or death. So that's why like outside of class, you kind of want to use your personal preference of what do you consider unusual, because what somebody might consider to be unusual, other person might not consider to be unusual. You kind of think about like if you ever gone like bungee jumping, like there's a certain percentage risk factor into going bungee jumping, but like some people take it, some people don't because they have different way of thinking about it. So we'll say E2 since all right, cool. And that's it. So for this class, what we're gonna consider unusual is less than 5%, but you just kind of know outside of class, that's kind of your own personal factor. Like some people are okay with being less than 5%, but other people might want it to be less than 1% or less than 0.1%. So it kind of just go up to you. All right. Any question in regard to the last prompt? All right, so let's go up. All right. So up next, we're gonna go over something called theoretical probability, and one of them is called empirical probability. So theoretical probability, you go like, in theory, this is what should happen, or this is the probability that we should get. So kind of the example I'm gonna give is flipping a coin. In theory, when we flip a coin, what are the chances that I land on heads? Cool, 50%. So that's what I got right over here. So whenever we're using theoretical probability, we're using kind of the theory, and the theory is you have one heads, two tails. So since one of them is heads, the other, and you have two options they could land on, you get 50%. When we use empirical probability is going based off of experiment. So we're not using theory that, okay, since this data set has 5 options and we only want one of them, it's 1 out of 5. What empirical probability is going, it actually does an experiment, and based off of that experiment, we come up with the probability. So in this case scenario, let me highlight it for you. It said if I toss a coin 10 times and get 7 heads. So for this one, if I want the empirical probability will either be 0.70 or 70%. Because for this one, we want to go based off of the experiment, not based on theory. So you do kind of want to tell the difference between empirical probability and theoretical probability. Theoretical probability is going based off of theory, based off how many options I have. This is how likely this event is of occurring. Empirical probability is going based off of an experiment that was done. And based off of that experiment, we could calculate the probability based off of that experiment. So theoretical probability is based off how many options we have. Empirical probability is based off of if we do an experiment and the probability of that experiment. Any question in regard to the definition of theoretical probability versus empirical probability? All right. So for this one, you're kind of going like, why do we have two models? So the real reason why we have two models is one of them, the theoretical probability is very hard to compute in real life. Because technically, in order to get the theoretical probability, you have to kind of do this infinite many times. So you can't really do the theoretical probability. Usually what you want to do, you want to use the empirical probability, and you want to use the empirical probability to conclude that the theoretical probability is correct. So you kind of want to use the empirical probability to self-check to make sure the theoretical probability is correct. Because that's the only way that you can kind of check to see if the theoretical probability is correct is by doing an experiment. And based off of that experiment, you want to check to see if the theoretical probability is correct. So kind of think about it. If we have a coin and we don't think that coin is fair, like you can't just say this coin is not fair. What you have to do, you have to do an experiment to prove that this coin doesn't follow the theoretical probability. Because if the coin is fair, it should be roughly 50-50%. But if the coin isn't fair, one of the two, either head or tail, would land more often. So usually we have the empirical rule to self-check that the theoretical probability is actually correct. All right. Everybody go for the theoretical probability versus empirical probability? All right, so here goes the formula. The formula is very basic, and so in order to find the probability, all you have to do is number of ways the event E can occur divided by the number of possible outcomes. So kind of you think about it like when we were doing what we call the male female for 2 baby horses. This one will just be, oh sorry. This one will just be how many outcomes do we have that satisfy that event? And the bottom one will be how many outcomes do we have in our sample space? So the bottom will be how many outcomes do we have in our sample space. The top will be how many outcomes do we have in our event. But that's it for that one. Any question in regard to that last, well, formula? All righty. So let's go all the way down. All right. So for this one, says a fair die is tossed. The result appear in the table at the left. So if you look at it on the left-hand side, it says the result. On the right-hand side, it says the frequency. So the result is me and landing on 1, 2, 3, 4, 5, and 6. The right-hand side is telling us the frequency. So telling us how many times did it land on 1, 2, 3, so on and so forth. So for this first one, it's telling us that the number 1 occurred 3 times. So if you go to the next one, it's telling us the number 2 occurs 6 times, so on and so on. Any question in regard to the table so far? All right. So how many times did he toss a fair die? So what's the total? Cool. And the way that you get the total, all you have to do is add up all these numbers. So let me just double check that. You have to be 100% confident. Oh yeah, 30. So for part A, it says based on the data, what is the empirical probability of tossing a 1? So how would I find the probability of tossing a 1? We'll just switch it around. So the probability that x is equal to 1 would be 3 divided not by 60 by 30. That should give you 1 out of 10, which is 0.10. So there's a 10% chance it will land on 1. Everybody good with that first one? All right, everybody good. So for the second one, it says, based on the data, what is the empirical probability of tossing a 2? So for 2, what should be the fraction? Oh, so you get 6 out of 30. 6 out of 30 is 0.20. Everybody good with 0.20 for part B. All right. So part C says, based on the data, what is the empirical probability of tossing a 3? So tossing a 3 is x is equal to 3. So for this one, you want to say 4 out of 30. If I do 4 out of 30, you get 0.13. And essentially, this 3 keep on repeating. So since they keep on repeating, I could just put a bar on top of it. You have to notify that it keep repeating. All right, so that's C. Let's do D. So for D, it says, based on the data, what is the empirical probability of tossing a 4? So say probability that x is equal to 4. So for this one, you say 6 out of 30. So if you do 6 out of 30, once again, you get 20%. All right, let's do the next one. So for E, it says, based on the data, what is the empirical probability of tossing a 5? So if you look at 5, for 5, it's going to be 4 out of 30, which is equal to 0.13. And the last one is F. We said, based on the data, what is the empirical probability of tossing a 6? There you go, probably x is equal to a 6 is equal to 7 out of 30. 7 out of 30, let me actually do that. I don't remember, or I don't know what that is. It's 0.23. So if you look at A all the way through F, all of these are empirical probabilities because we're going based off of the experiment that they did. Because this is a experiment. So since they did an experiment and since we're grabbing the probability from this experiment, this is an empirical probability. All right. Everybody good for the empirical probability portion of it? All right. All right, let's do G all the way through L. It shouldn't take that long. So for G, it says, what is the theoretical probability of tossing a 1? Okay, so we want to find the probability that X is equal to 1. So if this is the theoretical probability, it's going based off of theory. So how many ways when I'm tossing this die can I get 1? Well, there's only one way that you could get 1. How many different numbers are there in the die? 6. So you do 1 out of 6. And I think somebody already put the answer for this, but let me double check that. You should get 0.17. So, and that's the theoretical probability. So if you look at H, for H, what will be the probability for H? Remember the probability. Oh. 0.17, 0.17, 0.17, 0.17, and 0.17. Because since this is the theoretical probability, pretty much all of them have the same probability of occurring. Because if you look at 2, how many ways can you land a single die on 2? Well, there's only one way, because there's only one side that has a 2. So that one should be 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. Because in this case scenario, all of the sides are equally likely to occur. So you put 1 out of 6. All right, but that's it for that one. Any question in regard to the last one? All right. So up next, we're going to get into rolling 2 dice. All right. So for this one, what we're going to do, we're going to list out the sample space. But for this one, since the sample space is going to be pretty big, we're going to list it out using this table right here. So the sample space are going to be all of the outcome in this table. So when we're rolling 2 die, what we're going to do, we're going to focus on the summation of those 2 die. So pretty much where you're going to focus on the sum. So say if I want to get this one over here, what are the 2, well, if you look at it, is in this row and in this column. So if you look at the value for both of the die, both of the value for both of the die is 1. So for this one, if I do 1 plus 1, we get what? 2. Thank you. Then you get 2. What about for this one? Because now we're in the 1 row, but we're using this the 2 column. So that one should be 3. Perfect. What about this one over here? 4. And then this will be 5, 6, 7. Everybody good so far with that? All right, so now we're gonna go to the next row. So for the next row, we're gonna do this one with 2 and 1. So for 2 and 1, what the summation of those 2 die will give us? 3. So we go 3, 4, 5, 6, 7, 8. This one will be 4, 5, 6, 7, 8, 9. This will be 5, 6, 7, 8, 9, 10. This will be 6, 7, 8, 9, 10, 11. And lastly, we have 7, 8, 9, 10, 11, 12. So this is our sample space. So if I look at my sample space, how many total outcomes do I have? There you go, perfect. So you have 36 outcomes. All right. And actually that was part B. Oops, jumps ahead. All right. Everybody good on how we got that there's 36 outcomes? All right. And in case you're watching this later on, like the way that we got 36 outcomes, can you count how many total numbers you have? So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to this one, which will be 36. So that's how we got 36. All right, so let's do C. So C said compute the probability of rolling a 11 by random chance. So we want to find the probability that X is equal to 11. So how many different ways can we get 11? Cool, so there are 2 different ways. Out of how many? 36. So if we do 2, oops. If we do 2 divided by 36, you roughly get 0.0. Well, we'll just round it up to 6. So you get 0.06. And that's it for C. Any question on how I got C? All right, so let's do, yeah, perfect. So what we want to do, in order to find the probability of 11 occurring, what you want to do, you want to look at this table. So let me kind of erase some of this to kind of gunk it up. Oops. Let's do this more. Cool. So if you look at it, we want to find the probability that we get 11. So what you have to do, you have to look at this table and you see how many different ways can you get 11. So one way that you could get 11 is right here. So either this one can land on 5 and this one has to land on 6. So that's one way you could get 11. Other way you could get 11 is this one over here. So now this die land on 6 and this die land on 5. So if you look at it, there's only 2 ways that we could get 11. So that's why you put 2 right here. So then if you count how many individual numbers we have here, you're going to count that there's 36. So you put 2 out of 36, which is equal to 0.5555, la la la. But we just rounded that off to 0.06. Cool. And let's see. Okay. Yeah, no problem. Any further question in regard to C? All right. So if you're ever playing Monopoly or anything like that, so there's a 6% chance you could roll 11s. So let's do D. So for this one, say compute the probability of rolling 5 by random chance. So we're not looking at 11 anymore. What we want to do, we want to look at 5. So if we look at 5, well, let me erase the 11. Here go 5, here go 5, here go 5, here go 5. So how many different ways can get a 5? There you go, 4. So say probability of x is equal to 5, which is equal to 4 out of 36. So if we do 4 out of 36 in our calculator, we get 0.11. All right, and that's it for D. Any question in regard to D? All right. So for part E, it's a comment on the likelihood of rolling a 5 versus 11. So likelihood, you're saying, like, okay, look at the probability and you tell me, like, which one more likely to occur, which one less likely to occur. So which one more likely to occur? Yeah, so for this one, well, you want to say, here, I'll type it up for you. So we should say 5 is more likely to occur. So why is 5 more likely to occur than 11? Well, let's look back to just the basic of how do we get the probability. Good. So if you look at in the comment, it says there's more way that we could get a 5 compared to getting 11. Because if you look at 11, the only way that you could get 11 if you get a 5 or a 6, or if you get a 6 and a 5. But the thing is, for 5, there's actually more combination for a 5. You can get a 2 or 3, 3 or 2, but you can also get a 4 and a 1, or a 1 and a 5. So the reason 5 is more likely to occur because it has more options. So yeah, so it's not just the fact that it has a higher probability, because yes, it does have a higher probability, and the reason it has a higher probability because 5 has more outcome that could give you 5 versus 11 doesn't have that many outcome that will give you 11. All right, so let's look at F. So for F, it says for part C and D, would this be considered? Yeah, so would this be considered a simple event or a compound event? So let's focus on C. So we'll say, so for part C, which was 5, or sorry, which was 11. So is the event getting 11, is that a compound event or is that a simple event? And remember, simple event means there's only one outcome that give me that event. Compound event means there's multiple ways that I could get that event. Cool, all right, perfect. So this one will be a compound event. Because if you look at the outcome, how many outcomes give me 11? Well, the outcome that give me 11 are 2 outcomes. And those 2 outcomes are 5 and 6, or 6 and 5.
I think where I'm getting confused is because we're only focusing on getting 11. So that's why I'm thinking that's the one event is getting 11. But it's because there's more ways. Sorry, my bird's yapping. There's more ways of getting 11 than just one way. Is that what you're saying?
Correct. It's kind of going back to the event like getting one boy. Like, yes, we only want one boy, but how many different outcomes give me that one boy? And that's why that would be considered a compound event. Same thing for this one. We're looking for one number, but there's different ways that we could get that one number. So that why it'd be considered a compound event. So let's look at part D, which part D is the event that we get a 5. So for the event that we get a 5, would that be considered a compound event or would that be considered a simple event? Yeah, compound. For this one, how many outcomes do we have? Yeah, there you go. 4 ways or 4 outcomes. Good. All right, so let's do D. So for, oh, sorry, part G. So for part G, so when figuring out the probability, did you ever roll a die? So when we figure out the probability for 5 or 11, did we ever roll a die? Cool. So no. So would this be considered a theoretical probability or would this be considered a empirical probability? And remember, we never rolled a die. Yeah, so this one will be considered theoretical. So this will be considered theoretical probability because we never rolled a die. If I were to tell you I rolled 2 die 20 times and here's my result, then any information we get from that table will be considered empirical probability. But in this case, since I never actually did an experiment, it will be considered a theoretical probability. All right. All right, before we leave this example, for this problem, do we have any simple events? Like, can anybody see a simple event in this data set? Cool. So what about 2? So x is equal to 2. Yeah, 2. That's a simple event. Cool. We also got 12. Does anybody else see any other simple event? What about if I say one die has to be 1? So say this die has to be 1. So we'll say the left one. And we'll say the right one has to be 3. Technically, that will also be considered a simple event. Because technically, each one of these are a simple event. Because if I go more into detail and say like, okay, I want the first die to be a 5, the second die to be a 2, technically there's only one outcome that would give me that. So all of these individuals are technically a simple event. Just remember for a compound event means that you want multiple outcomes that give you that event. All right, but that's it for that one. Let's move on down. All right, so for this one, what I want you to do, I want you to practice on this one. Let's see, how many people do we have? So what I want you to do, I want you to practice on this one. And what I'm gonna do, I'm gonna try out this breakout room. So that way you could talk to some of your classmates. And I'll jump into the breakout room. So let's see, 1, 2. All right. So in a minute, I'm gonna break you up into 5 rooms. And once I hit create room, you're gonna get an invitation. You just click join on the invitation. And that way I'll kind of jump around to kind of answer any question. So let's create the room. All right. So you should be getting an invitation right now. So as soon as you get the invitation, you just join it. And that way you could join your room and you could talk to one another. Oh, cool. Mostly everybody's done. Let's join this one. Okay. So how are we doing with this example? Anybody here? Yeah, the breakout room are a little bit weird, but all right. Any question in regard to this problem? Okay, yeah. All right. Well, if you need any help, I'm here. Just chat me up, and I'll help you out. So let me see. Let me go on to the next one. All right. How are we doing? Let's see. Awesome. Any question about any of the 3 parts? Also, just know if you want to just talk, you can just unmute yourself. So, what question do you have, Emmy?
So the last one, the likelihood of the candy being yellow versus blue by random chance. So so blue is, there's only 2 blue candies versus 6 yellow. So there's gonna be, you know, the yellow is, there's 3 times more chance than the green candy, right?
All right.
I don't know.
Yeah, so you just want to say, like, since yellow has more outcome available to it versus the blue, which only had 2 outcomes, like the yellow one's more likely to occur. So there's more chances that we get a yellow one versus getting a blue one.
Okay, so I just say 3 times more likelihood.
You can just say pretty much sorry, that the yellow is more likely to occur just because it has more options.
Oh, okay, got it. Okay.
Yeah, you don't have to say like 3 times or 5 times. Just say it's more likely to occur, and that's perfect.
Okay, got it.
Yeah. All right. Any other questions?
Question. So why, if yellow has a higher chance, then why does it have a lower percentage?
Come here, man. You shouldn't have a lower percentage because how many total candy do we have?
So there's 30 total, right? So we divided 6 divided by 30. It was 0.20.
Yeah, 0.20. So then,
And then if we do the blue, there's 2. So then 2 divided by 30. It's, oh, okay, got it. It's 0.06.
yeah,
And I wrote 0.67.
Yeah, no, we all know birthday.
Okay, got it. Thank you.
All right, let me go hit up the other room.
Hi. Can hear, we can't hear him, right?
Sorry,
Yeah.
every time I go over, it mute me for some reason. Any question on the problem, or we're all good with it?
No, I think we got it, right?
All right, cool. So there's no question. Let me go do the last room, and then we'll all come back together.
Okay.
Okay. Keep it up. Hey guys, how are we doing? Or you can just unmute yourself if you want to say something.
We were just kind of waiting.
Okay, so you're all done.
Yeah,
No.
I'm done.
I couldn't see anything.
I didn't see anything. I just saw it was just like the screen that said, just kind of like when you start a Zoom meeting.
Okay.
Well, now it's showing something.
Yeah, for some reason it stopped showing me.
Oh, there it is.
There it is. Yeah.
Yeah, sorry about that. So I'll leave that.
Guys, doesn't this look like a double angle identity?
Break up. All right, so let's go ahead and do this problem. So for part A, it says, what is the probability by random chance that it is yellow? Yeah, get the chat going. Cool. So we get the probability that this candy is yellow is equal to 0.20. Okay. What about the probability that the candy is a blue candy? Yeah, so you have to be careful, Emmy. You forgot to put the 0 in front of it. So the probability that x is equal to blue is equal to 0.0. Well, if you want, you can say 0.07. Okay, if you look at it, 0.0666, so technically the 6 will round up the other 6 into a 7. All right, so for this one, comment on the likelihood of the candy being yellow versus blue by random chance. So which one more likely to occur, yellow or blue? So say yellow is more likely since So for this one, we'll say yellow is more likely since it has a higher probability. And that's it. Any question in regard to this problem? All right, so let's add a question to this one. So based off of the part A and part B, are these theoretical probability or are these empirical probability? All right, so we have one empirical, we have one theoretical, now two theoretical, now two empirical, so now three empirical, and now we have oh no, and now we have three theoretical, three empirical, four empirical, three theoretical, and now we have 4. Now we're tied. Now we have 5 empirical, now we're tied again. Okay, so for this one, well, for this one, if you look at it, for the experiment, are they doing an experiment?
Yes, experiment.
Yeah, because they're doing an experiment because they got a fun side candy M&M. So for this one, they're actually doing an experiment because they did an experiment where they open up the candy and they went like, okay, we have nine brown candy, we have 6 yellow candy, we have 7 red candy, we have 4 orange candy. So for this one, since they actually did an experiment, because they actually told us, hey, we got a fun side bag of M&M, and they open it up and then they started notating because they told you the result. Both of these will be considered empirical probability. Because theoretical probability would have been like, hey, we have these 5 candy color. So since we have 5 candy color, we'll say each one of them has a 1 in 5 chance of occurring. Is it at the same amount? Yeah, so if we would have said that every bag had the same amount of candy or the same amount of colored candy, then yeah, we'll say it's theoretical. All right, cool. All right, so I think we're done with that. Any question in regard to this last problem? All right, so let's scroll on down. All right. So up next, we're gonna get into something called a Venn diagram. So a Venn diagram, kind of think about, if you remember, we did a tree diagram where we did pretty much the gender of the baby. If you want, you talk to me at the end, Emmy, I'll try to unconfuse you. So what we're gonna do a Venn diagram, and for the Venn diagram, it's kind of like a tree diagram where you're supposed to kind of visually be able to see the data set. So for the Venn diagram, in our case scenario, usually you could do multiple events, like 3 events, 4 events, 5 events. There's kind of like no limitation to how many events you could do. But for us, we're only gonna focus on 2 events. So if you look at our 2 events are A and B. So when we do a circle, the circle represents the probability of that event occurring. So if you look at this circle represents the probability of A occurring. If you look at this circle over here, that represents the probability of B occurring. But if you look at it, this is the middle portion. This middle portion is the overlap. So the overlap represents the probability that A and B occur at the same time. And this is what this is representing. So this symbol right here represents AND. So whenever you see that symbol, it just represents the AND symbol or the AND statement. So just remember, for a Venn diagram, you're gonna have 2 events. The 2 circles represent those individual events. And if your 2 events overlap, that means they have something in common. So that means both of those events could occur at the same time. So when I say that both of the events could occur at the same time, kind of think about like if somebody has an umbrella and it's raining, those two events could occur at the same time because there could be an occasion where somebody has an umbrella and it actually is raining. So when we say the and statement just means both events are occurring at the same time. Any questions so far for this Venn diagram? All right. So up next, we're gonna focus on a Venn diagram when we have disjoint event. So when we talk about disjoint event, it just means we have two events and they don't have any overlap. So here is the Venn diagram for that one. So if you look at this Venn diagram, we have event A, we have event B, but since they're disjoint or mutually exclusive, they don't share any overlap. So they're not overlapping, and that's why they don't have this middle portion right here. So that's what two events is. So two disjoint event or mutually exclusive event are yet two events that cannot occur at the same time. So kind of think about it, let's go back to the scenario where we have the guy with the umbrella. So event A could be the person has the umbrella, and event B could be the person does not have the umbrella. So if you look at it, those two events cannot occur at the same time because either the person has the umbrella or they don't have the umbrella. It's not possible for that person to have the umbrella and not have the umbrella at the same time. So those are mutually exclusive events. It is two events that don't overlap. All right. Any question in regard to mutually exclusive event? All right, so I'm gonna go over some example of some mutually exclusive event. All right, so here go my sample space. So here go event A. So event A is including, so sample space is listing out all of the number it could possibly be. So for my sample space is saying it could be any number from 0 all the way to the number 9. So for A is saying it can either be 0, 3, 5, 7, 9. If you look at B is saying it could be either 1, 2, 4, 6, and 8. So what we're looking for, we're looking to see if they have any overlap. If they have overlap, then this is not mutually exclusive. But if it doesn't have overlap, then we could say it's mutually exclusive. So if you look at A and if you look at event B, do they have any event that they share? Well, what do they share? If they share. Yeah, because if you look at both of the events, since like, if you look at 0, did this one have 0? No. If you look at 3, does this one have 3? No. This one has 5? This one doesn't have 5. This one has 7? This one doesn't have 7. This one has 9? This one doesn't have 9. So this one is a mutually exclusive event. All right. So that's that first example of mutually exclusive. Any question for this first example? Let's do the second example. All right, so we have event A pet is a dog. Event B, a pet is a cat. Event C, a pet is a bird. So for this one, the sample space is you have a singular pet. So for this one, is it possible if I only have one pet, for that pet to be a dog, a cat, and a bird at the same time? No. So it is possible for one pet to be all of those three things. So remember, we have one pet. That's my best drawing of a pet. So if we have one pet, Is it possible for that pet to be all of those three things all at once? No. So that's why this will be considered mutually exclusive, because if we do a Venn diagram, it's either going to be people who have a dog, people who have a cat, or people who have a bird. But it's not possible for one pet to be all of those three things. All right. Any question for that second example? And right now we're gonna do mutually exclusive, and then we'll be done for today. So I'm gonna skip this example. We're gonna go to this one. Yeah, what's your question? Do you have a question, Cameron? I think sure the sample. Well, because if you look at, so say we have A right here. So this is event A. Event has 0, 3, 5, 7, 9. And then you have event B. Which is 1, 2, 4, 6, and 8. Since A and B have nothing in common, that's why we say mutually exclusive. Because they don't share any of the same number. Because if you look at A, it's 0, 3, 5, 7, 9. But if you look at B, it's 1, 2, 4, 6, and 8. Since both of them don't share any of the number, that's why they're mutually exclusive. If it wasn't mutually exclusive, you would have the same number in both A and B. So that's how you can kind of tell if they're mutually exclusive. If you have both of the value in both of them. Yeah, S, if you remember S just stands for the sample space. So always putting the sample space for you right here. Yeah. Perfect. All right, so I'm gonna skip the one about baseball, because for baseball, you could either win a game or you could lose a game. So it's pretty straightforward, I hope. So for this one, we put A, car brand is a Honda. B, car brand is a Kia. So for this one, it's mutually exclusive because your car is either going to be a Honda or your car is either going to be a Kia. But it's impossible for your one car to be a Honda / Kia. It's going to be one or the other, but it's not going to be like a Honda Kia. It's not going to overlap on each other. Any question in regard to the Honda / Kia problem? Okay. All right. So for this one, I'm going to get into examples that are not mutually exclusive. So for this one, there are overlap. So for this one, if you look at event A, a person gets struck by lightning. B, a person doesn't get struck by lightning. Oh, sorry. This one is still, that one's still mutually exclusive. Sorry for that. So for this one, if you look at it, a person gets struck by lightning, or event B, a person doesn't get struck by lightning. So those are mutually exclusive because you're either going to get struck by lightning or you're not going to get struck by lightning. So that way that will be considered mutually exclusive. All right, so we'll do these last one, and then we'll save the other one for tomorrow. So for this one, it said heading west and heading east and west at the same time is impossible. So those are mutually exclusive because you could either have west or you could have east, but it's kind of impossible for you to be heading east and west at the same time because they're pretty much opposite direction from each other. Another example of mutually exclusive event, tossing a coin and getting head and tail at the same time is impossible. So both of those events are mutually exclusive because your coin is either gonna land on heads or it's gonna land on tail. Another example of mutually exclusive is you can't take the bus and the car to work at the same time. So both of those events are mutually exclusive because you're either gonna take the bus to work or you're gonna take the car to work. But it's not possible for you to take the bus and the car to work at the same time. All right, so let's see the last two. You can't get a pay raise and a pay decrease at the same time. It's either gonna be one or the other. They're kind of mutually exclusive because either you're gonna get a raise or you might get a pay decrease, but it's impossible for you to get both of them at the same time. And the last example that I have, your dog can be both a purebred dog and a mutt. It's either a purebred dog or is a mutt, but it's impossible for it to be both because they contradict each other. Because a purebred means that it's not mixed, a mutt means it is mixed. So these two are mutually exclusive from each other. All right, so those are my example for mutually exclusive. So mutually exclusive means both events cannot occur at the same time. It's either gonna be one or the other, but it can't be both at the same time. All right, any question in regard to mutually exclusive? All right, so let's stop the share. Let me put a little note right here. Stop share. All right, so that's pretty much it for today. So just remember for tomorrow gonna be Wednesday. Wednesday is gonna be the day that I'm gonna use that material to pretty much construct the quiz that you're gonna take on Thursday. So you do want to pay extra attention tomorrow, because whatever I go over tomorrow, that's what's probably or most likely gonna be on the quiz. So nothing that I went over today will be on the quiz. It's pretty much just whatever information we go over tomorrow. So do pay attention on what we go over tomorrow, because anything that I go over tomorrow could be on the quiz. By tomorrow, I should have most of your tests corrected by then, if not all your tests corrected. And I'll show you where you're gonna submit the test correction if you do wanna do test correction. All right, but any questions before I close out this meeting?
Question. So if we got a test grade today, that's our grade, right? Like you already graded it?
Correct. The only thing I could add, if you email me any of the tests, like the box plot, I still need to go through all of my email and see all of the pictures of the box plot. So if it says everything been graded, then everything been graded if you didn't email me the box plot. All right. Any other questions? Cool. What's your question, Camera? Cool. All right, so let me do, what about the picture? Yeah, the question at the end, it was just pretty much just to verify that it's you taking the exam, but there's no points related to that one. So if you didn't upload it, it didn't really matter towards your test grade. Yeah, I didn't take away any points away from it being late. Cool. All right. So let me see. Let me answer Emmy question, then I'll get to you, Anna. What question did you have, Emmy?
So Javier, he said this. I'm a little confused. If the same amount of every color in every bag, then it would be a theoretical. Why is that?
Well, because if you remember theoretical, we assume all options are the same.
Oh, okay, got it.
Yeah,
okay.
So for theoretical, because kind of like theoretical, we can only go like, okay, we have 10 different colors. So for theoretical probability, we're gonna say all of them have the equal chance of occurring. So brown, blue, green, red, we're gonna say all of them have an equal chance of occurring. So that way, for that one, we'll say theoretical probability.
Oh, okay, okay.
But-
Okay.
But
Uh-huh.
if we get it from a bag that we open up, it will be considered empirical probability.
Got it. Okay. Sounds good. Thank you.
Yeah, you're welcome. Anna, you had a question? Oh, the quiz? No, the quiz. If you know the quiz, if you know it for chapter four, we finished that. I forgot when we finished it. We finished it on Tuesday. So none of chapter 4 will be on the quiz. It purely going to be what we go over on tomorrow. So pretty much what's going to be on the quiz tomorrow is going to be chapter 5. So chapter 5, what we're going to go over tomorrow. Correct. Yeah. Yeah, because right now I have all of the exam closed because I just wanted to make sure nobody got their exam and people were still taking it. So yeah, so I'll open it up once I have everybody graded. So yeah, so they should be open up by tomorrow. Test 2. Let me see. What does my syllabus say? Syllabus. Where is that syllabus? We should have test number 2 probably somewhere like in week, what is that, 5? Because right now, what are we? We're in week 3. So yeah, so we should be finishing up with most of chapter 5. Next week we'll go over chapter 6, and then pretty much you should have it probably somewhere in week number 5. So by week number 5, you should have test number 2. Yeah, hopefully, if everything stays the same. All right, any other question that you're dying to ask? All right, so I'm going to close out the meeting. If you missed anything, I'll upload the notes and I'll upload the video onto Canvas. It'll probably be uploaded by midnight tonight. So if you do want to watch it, it'll be up somewhere like at midnight tonight. All right, so that's it for today. Have a good night, and I'll see you tomorrow.